Unit 9 review. If a ball of mass 3 kilograms moving at 2 meters per second eastward, I'm going to call, let's see, east is like that way, so I'm going to say that that's positive. Strikes head on a ball of mass that is moving this way westward, so I'm going to call this negative. The balls stick together after the impact, balls of clay or something. Complete the momentum conservation diagram. What's the magnitude and direction of the velocity of the combined mass after the collision? All right, so at the start, I've got the ball of mass 3 and ball of mass 1. I'm just going to subscript them like that, their masses. This one's moving to the right, and this one's moving to the left. Now, if you're wondering to yourself, why did he make this one bigger than that one? How did he know that? Why did he know that? Is he right about that? Well, I just did some real quick math here. 3 times 2 is 6. That's the momentum in the east direction of the first ball. And 1 times 2 is only 2. So this is going to have like positive 6, negative 2. Those are the different momentums of the two balls. So that's what I'm representing here. Yeah, sometimes you have to do some math, you know. I don't know what to tell you. 1 plus 3. So they stick together. And then the thing I know here now is that 3 minus 1 is 2. Got to have the same amount of stuff. I got a positive 3 and a negative 1, so it gives me a positive 2. Okay, what's the equation look like? I've got the momentum of ball 3 plus the momentum of ball 1 at the start, and that's going to be equal to their combined momentums, because, well, there's only one because they're stuck together. So the mass of the 3 kilogram was 3, and it's going positive 2, plus the mass of the little one is 1, its velocity is negative 2, and then the mass of them when they're stuck together is 1 plus 3 times, I don't know how fast they're going, but we're going to find out in just a second. I think if we do the math here, 6 minus 2 is 4, divided by 4. It's going to be 1 meter per second. In the positive direction, notably in the positive direction. All right. I think I might have mentioned this situation earlier in some notes or something. One way of measuring the muzzle velocity of a bullet is to fire it horizontally into a massive block of wood that's placed on a cart. Assuming no friction, we can then measure the velocity which the wood containing the bullet and the cart begin to move. Actually, that works whether or not there's friction, as long as you get the initial velocity of the cart. In one experiment, the bullet has a mass of 50 grams. The wood and its cart had a mass of 20 kilograms. After the shot, the cart, the wood, and the bullet moved at a constant speed, traveling 8 meters in 4 seconds. Okay, so they're giving us this, so we would have to assume no friction, that it's not slowing down. So 8 meters in 4 seconds, 8 meters in 4 seconds is 2 meters per second. Okay, so this is a collision, to be sure. And I've got a bullet. And I've got that. I'm just going to call the cart with the wood block on it, I'm just going to call that whole thing cart. So at the beginning, I'm going to say the bullet's going in the positive direction. We'll give it a big 4 bars. It's going so fast. And then after, everything sticks together. So I've got the bullet and the cart. That's it, stuck together. Like that. momentum conservation equation, I've got the momentum of the bullet before the collision is equal to the momentum of the bullet and the cart after the collision. And from these data, complete a momentum conservation diagram and determine the original speed of the bullet. So the mass of the bullet, 0.05 kilograms. Grams is not the right units. Times, I would like to know its initial velocity. And then afterwards, the mass of the cart plus the bullet times the meters per second. Okay, so just need to multiply those together, then divide by 0.05. Gives me about 800 meters per second. All right. Raft of mass 180 kilograms carries two swimmers of mass 50 kilograms and 80 kilograms. Raft is initially floating at rest. The two swimmers simultaneously dive off the opposite ends of the raft, each with a horizontal velocity of 3. They're diving off opposite ends, so they got to be going opposite directions. We'll say that this one's going to go in the negative direction, and this one's going to go in the positive direction. How about that? Okay, this is an explosion because everything is all together at the start, the raft and the two swimmers, and then things go flying apart. So I got the raft and the swimmers. I can put them all together on the same line because they're all stuck together. And they're not moving. Here, everything separates. So I got the raft, I got swimmer with 50 kilogram mass, and then the swimmer with the 80 kilogram mass. So what's going to happen? Well, let's see. If the 80 kilogram one goes in the positive direction, if I gave that swimmer 3 bars, then this one going in the other direction would have to be not as much because same 3 meters per second, but less mass, and that means the raft is going to have to take up the last bit so that this positive 3 can be balanced by negative 3. Okay, so the momentum of the raft plus the swimmers before is going to be equal to the mass of the raft plus mass of swimmer 50 plus mass of swimmer 80. This is 0 because everything's just motionless at the start. And then the momentum of the raft is the mass of the raft times the velocity of the raft, which we don't know, plus the mass of the 50 kilogram person times their velocity of negative 3 meters per second, right? And times the mass of the other 80 kilogram person, and they're going positive 3 direction. All right, so time to do math. That's going to be, I think, you're going to get that the VF is negative 0.5 meters per second. What does the negative sign mean? That means it's going in the same direction as the lighter swimmer, which makes sense. All right, cruising right along. Find the momentum of each of the following objects. Okay. should be easy enough. Momentum is equal to mass times velocity. Gotta have things in the right units, though. So 50 kilogram ball, that's right units, and that's the right units. Okay, so I just multiply those together. 8 kilogram meters per second. Great. 20 gram marble, that's 0.02 kilograms. With a velocity of 10 centimeters per second, not the right units, that's 0.10 meters per second. And then I can multiply those two together, so that's 0.002 kilogram meters per second. Okay. Then I have a 1,500 kilogram car. That's the right units. 65 miles an hour. That's not the right units. We just did a conversion like that a few minutes ago. Where did it go? There it is. To change from miles per hour to meters per second, you multiply by 1,600 and divide by 3,600. So I'm going to do that. 65 times 1,600 times 3,600, sorry, divided by 3,600. That 29. Okay, so my momentum is going to be 1,500 times that, because momentum is just mass times velocity. It's about 43,000 kilogram meters per second. All right. A golf ball of mass 215 grams. Wrong units. Has a velocity of 41 meters per second. Okay, that's the right units. What velocity must a 1.2 kilogram ball have to have the same momentum and the same kinetic energy? Okay, well, the momentum of this is equal to 0.215 times 41, about 8.8 kilogram meters per second. And we want to know what velocity must a 1.2 kilogram ball have. So that would be, if we made that the momentum of the momentum of the ball is its mass times its velocity. And we would do a little bit of mathing there. That's 7 point, no, is that right? Yeah, I guess that's right. 7.3 meters per second. How about the same kinetic energy? Well, EK is equal to 1/2 mv squared. That's 1/2 the mass times the velocity squared. Okay, so that EK is 1/2 times mass times velocity squared. About 180 joules. And now I want to know, okay, what about this 1.2 kilogram ball? What if I had that? What velocity would it have to have that much kinetic energy? So 1/2 times 1.2, and then divide that over. That's about 300. So that's, oops, sorry, I'm off screen there. That's interesting to think about for a minute. You got a golf ball with this velocity. If you want to have the same momentum with a 1.2 kilogram ball, you only need to be going this fast. If you want the same kinetic energy as the golf ball, then you have to be going that fast. Oh no, not true. Forgot to square root. You have to be going the square root of that fast, which is still bigger than this. So it's, instead of 7.3, it's 17.3. Yeah, that was freaking me out for a second. So you want to have the same kinetic energy, going to have to be going faster. All right. 145 gram baseball, wrong units. There we go. Approaches a batter with a velocity of this. If the bat and baseball are in contact for this long and the baseball leaves the bat with a velocity of this, how much impulse was delivered? Okay, you got to be careful here. I'm going to say that the baseball's approaching the batter, that's the negative direction, and that the batter hits it and then in the positive direction. This is the number one mistake that I see my physics students making with this kind of problem, is not respecting the different directions there. So let's see, I've got force times delta T equals mass times delta V. So force times 0.062 is equal to mass times the change in velocity. The final velocity is 25 minus initial velocity. So I'm going to do this side and then divide by that. .140 newtons. Oh, wait a minute. That was the answer for this. How much force? How much impulse? That's just this side. If you can find this side is equal to impulse, this side, well, they're equal to each other. So if this is an impulse, then that must also be impulse. So I'm just going to go back and do that side only. And that gives me, that's 8.7 kilogram meters per second. And then finishing the problem there. 140 newtons of force. All right. A 2,100 kilogram car traveling at 30 meters per second brakes for 5 seconds with a braking force of that. How fast is the car traveling at the end of the 5 seconds of braking? So force times time equals mass times change in velocity. The force is this. I'm going to call the braking force, I'm going to say that's the negative direction. The car is going in the positive direction, and the braking is in the negative direction. Got to respect the different directions. So the force, negative 3,500, times time is 5 seconds, is equal to mass of the car. Final velocity, I don't know, minus initial velocity is 30. So got me another algebra problem. Well, let's see. I'm going to write out one more step here. That's minus 17,500 is 2,100 VF minus 30 times 2,100 is 6,300,000 rather. Add that over to there. And then divide by 2,100. It's about 20, I'm going to round that to 22 meters per second. Better hit the brakes harder than that. Well, maybe that's all they wanted to do, just slow down that much. If you didn't do the signs right, it's possible that you went through this and you got, okay, the car's going 30 meters per second, and then I hit the brakes and then it's going faster. And that just cannot possibly be right, because brakes don't speed you up. All right, so that would point you, that would make you think, okay, I must have made a sign mistake somewhere, and then you can think very carefully about what's going on. Hopefully catch your mistake. Two carts with masses of 4 kilograms and 3 kilograms move toward each other. Okay, one of them's going in the positive direction, one's negative. I'll call this one positive and this one negative. They move toward each other on a frictionless track with speeds of 5 and 4. So that's the plus 5 minus, right? They don't have masses, sorry. I should have put the positives and negatives with the velocities, not with the masses. The carts stick together after colliding. Okay, so I've got the cart with a mass of 4, and I've got the cart with a mass of 3. I said that the one with the mass of 4 is going in the positive direction, and 4 times 9, that's 20, and this one's got, so this one's going to be more than that one. Again, I just did the numbers real quick there. 4 times 5, that's positive 20 momentum for that one, and this is going to be negative 12. So that helps me get this right. This is a collision, good old-fashioned cart collision, and then they stick together. Okay, well, if I've got a little bit extra in the positive, I've got 4 minus 3 is positive 1 for the carts stuck together. What's the final velocity of the carts? I'm going to write my conservation of, oh, there it is, conservation momentum equation. So the momentum of 4 plus the momentum of 3 is equal to the momentum of the two stuck together. So mass of this one is 4, its initial velocity is 5, mass of the other one is 3, its initial velocity is negative 4, it's going the other way, and then they collide, that's their total mass, times, don't know how fast they're going, that's what I'm looking for. So it looks like, do a little bit of math, I should get about 1.14 meters per second. What's the impulse delivered to the 4 kilogram cart? Well, let's see, the 4 kilogram cart's going this way in the positive direction, so the impulse on it is going to be negative. But we can just do the impulse delivered to the 4 kilogram cart is the mass of the 4 kilogram cart times its change in velocity. Its mass is 4. Its initial velocity was, its final velocity is this, minus its initial velocity was positive 5. So it's about negative 15.4 kilogram meters per second. Now the impulse on the other one has to be exactly the same. So just to check, this is not asked in the problem, but I'm going to do the mass of the 3 kilogram cart times its change in velocity, and I better get the same thing. That's 3 times its final velocity is the same, 1.14, minus its initial velocity. It was going 4 in the other direction. It was going negative 4 to start. So let's math that. You can enter it in your calculator just like that, even with the double negative sign, minus negative 4. Hey, it's 15.4. But positive, and that's Newton's third law, right? Equal and opposite. Last page. All right. 2 cars headed toward stop signs. Car B was going this way, and car A was going this way. And they collided with each other and ended up kind of like this. Accident investigators come upon the following scene involving a collision between two cars similar mass. Both drivers had intended to travel through the intersection without turning, so they were trying to go straight. Driver A says that after stopping at the stop sign and then proceeding, car B ran the stop sign, so there was no time to stop before hitting the side of car B. But driver B says that after stopping at the stop sign and proceeding, car A came out of nowhere, evidently running the stop sign and T-boning car B. Which car ran the stop sign? Well, which one had a greater change in momentum? Well, let's see. They had the same change in momentum, right? So the collision is in the one direction and the other direction. You can see that the change in the velocity of this one in this sideways direction is pretty small, which means that car A had a pretty small velocity in this direction. The change of this car velocity in this direction is bigger, which means that this car had a greater velocity in this direction, right? That it like kind of dragged that car along with it. So who ran the stop sign? Car B. How do we know? Because greater change in momentum in B's direction. Sketch a picture of how the cars would have come to rest had the driver's story that ran the stoplight been true. Oh, it's not a stoplight, it's a stop sign. Sorry about that. Okay, so if car B, was really telling the truth and they stopped and pulled out, and then this car came zooming through, then they would end up like over here, because the higher velocity of car A, that would have a greater input on the momentum. They're going to end up over here. So like A, let's see, B would probably be like something like that, and A would be like crashing into it over here. So A didn't change that much off its course, and B got taken way more off its course. They're still going to have an influence on each other, but whichever one's going faster is going to have a greater influence. So if A is going faster, that's going to push them this way more than it pushed them up. So A didn't divert that much from its path. B diverts more from its path. That means A had more momentum. There you go.